It's our great pleasure to introduce Jeff Prosise. Jeff?
Many of us learn from his books.
Yeah, definitely. So Jeff has, I think, decades of experience as a software engineer, trainer, author. And I think, yeah, we're laughing before the conference because yeah, he's also famous for co-founding Wintellect, which is a well-known company. But then, yeah, although he wrote several books, I think it's around 9. Yeah, I vividly remember I think it's the first one. It's the programming Windows with MFC, and I read that when I was in college. And then I also was extremely happy that a few years later .NET came around, and yeah, I could move into that.
That's probably one of the explanations why this book is so well known, because it helped us a lot with MFC and dealing with all the intricacies and then sophisticated things at that time, at least, and the platform.
So Jeff, welcome to CodeCamp.
Thank you. Great to be here. Great to see both of you this morning as well.
All right, so we're getting ready to start your session, which yeah, I can hardly wait for, because it's a complex problem like image classification, which has been one of the big problems that AI tackled. But then we're trying to solve it, or we're solving it now with ML.NET. And for me, that's important because ML.NET, I think, opens this ML or AI space to more developers. So I'm looking forward to it from that perspective as well.
We're going to have some fun.
Well, you can share your screen, and you have the floor.
Thank you so much. And quick question for you. I have my webcam attached. Can you see it?
No. I was going
Interesting. Interesting. It must be a Teams thing, but you know what? The good news is it doesn't matter whether you can see me or not, as long as you can hear me and you can see what's on my screen. And can you see the cover slide right now, just to be sure?
Yes,
okay, perfect.
All good.
Well, thank you so much. We have 45 minutes together. Let's try to make the most of this. The title of this presentation is Building Sophisticated Image Classification Models with ML.NET. And just a quick bit of background. Much of the last 4 or 5 years of my career have been spent studying machine learning and AI, and I'm honestly having more fun right now than I've had in many, many years. I love these things, and what I especially love about these technologies is that we can bring them to the world of software development and use them to solve problems that would be difficult, if not impossible, to solve by conventional means. In fact, one of those problems is that of image classification. If you're working at a company that builds a self-driving car, for example, how do you write software that looks at frames coming from a video camera in that car and tells you whether there's a person in front of the car in a crosswalk, or a stop sign, or a red light, or something like that? Or maybe you work for a manufacturing facility, and you take pictures of every part that rolls off an assembly line, and you want to determine through software which of those parts are defective and which are not. Those are classic applications for image classification. And the good news is it's not real hard to solve those problems today. Typically, they're solved in Python. We're going to solve them in ML.NET, but we're first going to learn a bit about how cutting-edge image classification works by looking at neural networks and by looking at them in Python. So I want to start just by saying a word about neural networks. You've probably heard of them. You may or may not have done anything with them, but a traditional neural network is simply a bunch of neurons arranged into layers like the ones you see right here. The circles represent neurons. In this example, the neural network has 3 layers. There's an input layer where we provide 2 inputs when we want the neural network to do a computation. And there's an output layer which contains a single neuron, which implies that in this case, it's going to somehow transform those 2 inputs to produce a single output. The computational work is done in the so-called hidden layers between the input and output layers. And even though neural networks can be a little bit scary math-wise, especially when it comes to understanding how neural networks are trained, once a neural network is trained, the way it works is pretty simple. Each one of these neurons is assigned a value that we call a bias, or B for short. And every connection between every neuron in adjacent layers is assigned a weight, which we refer to as W. When I run this neural network, when I ask it to do a computation by providing two inputs, values X and Y, all it does is propagate those inputs through the network to the output neuron. And the way it does the propagation is very simple. For each connector, each arrow, if you will, between the neurons in the input layer and the middle layer, the hidden layer, it multiplies the value of that neuron, X, by the weight that attaches it to the next neuron in the next layer. It literally just propagates those values through, sums them up, adds the B or bias values assigned to each neuron to come up with an output. Maybe this neural network is designed to add numbers together or multiply them or do something else. Whatever it does, all of that is encapsulated in the math that goes on in the middle. One thing that's important to understand about neural networks is that if we simply multiplied numbers, added them together, and propagated them through the network, neural networks would be very good at solving linear problems, but they wouldn't be so good at solving nonlinear problems. Think nonlinear equations like polynomial equations. So the trick that enables a neural network to do nonlinear computations is something called an activation function. Essentially, from that first hidden layer on, when a value is propagated to the neurons in the next layer, we first run the value through an activation function. There are four popular activation functions. They're very simple ones. They're shown here. The one that's used the most often in middle layers is the ReLU function, which stands for rectified linear units. And basically all it does is get rid of negative values. It turns them into zero. It's a very simple nonlinear transformation, but again, the presence of these activation functions enables these neural networks, which mostly just do linear math as values propagate through, to solve very nonlinear problems. Now, that's a traditional neural network. State-of-the-art image classification is typically not done with that kind of neural network. Instead, it's done with a type of neural network called a CNN, which stands for Convolutional Neural Network. This diagram shows what a typical CNN looks like. And out on the right-hand side, there are so-called FC layers. FC stands for fully connected. Those are just layers of neurons that are connected together, exactly like the neurons you saw in the previous slide. But before the fully connected layers are a series of convolution layers and pooling layers. The purpose of a convolution layer is to extract information from the image. We say extract features from the image. The purpose of a pooling layer is to subsample the image. We typically cut it down to half of its present size. Then we run that subsampled image through another convolution layer. We extract features at that resolution. We run it through another pooling layer to shrink the image again and rinse and repeat. Now, I want to show you what this actually does and why convolutional neural networks are so often used to solve state-of-the-art computer vision problems. What the convolution layers in a convolutional neural network really do is what the literature refers to as feature mapping. Generally speaking, that means edge detection, and it relies on a technology that's been around for 50 years or more, which is image processing with convolution kernels. This is how, by the way, Photoshop sharpens images, blurs images, detects edges in images, and things like that. As an example, look at the hot dog image on the upper right here. I take a convolution kernel, which is that 3x3 array of values whose values add up to 0, by the way, because we don't want to add or take away information. And what I do is I run that kernel over every pixel in that hot dog image. And as you can see on the left, what I do is multiply the pixel value under a cell of the convolution kernel by the value inside it. I sum those up and I replace the pixel in the middle with the computed value. If I run the convolution kernel that you see on the right over that hot dog image, the image that you see in the lower right is the one that is produced. You can see that I found the edges in the image, and this is the secret to how convolution kernels work. They ignore most of the information in the image. They ignore a lot of subtleties. What they do not ignore are the features, the edges that define whether this image might contain a hot dog or a hamburger or a cat or a dog or something like that. Now, you and I can build convolutional neural networks fairly easily. You can build them with TensorFlow, PyTorch, and other deep learning libraries, or more often they're built with an open source Python library called Keras, which uses other deep learning frameworks as its backend. By default, it uses TensorFlow as its backend. In fact, the gentleman that created Keras was hired by Google, and Google, who created TensorFlow, now recommends that you not use the TensorFlow API directly, but instead use Keras, because you can build a convolutional neural network with Keras and maybe 10 lines of code. It's going to take you 100 lines of code and a much deeper understanding to do the same thing in TensorFlow. But this is what a convolutional neural network might look like in Keras. I start off with a pair of convolution and pooling layers. In other words, I'm going to run, in this case, 5x5 convolution kernels over the input images. I'm going to subsample the image twice to cut it down to size. So I'll basically be extracting features at the image's original resolution and at half of its normal resolution. Then I define with the calls to model.addDense the hidden layers, the fully connected layers that look at the features that are coming out of the convolution and pooling layers and correlate those to a problem, like does this image contain a hot dog? Does it contain a cat or something like that? Now this works. You can, if you have TensorFlow and Keras installed on your machine, or maybe in a VM, you can go type in this Keras code and you can run it, and it'll work. The problem is, to do state-of-the-art image classification, what self-driving cars do, for example, the models are typically trained with millions of images, and it's incredibly CPU intensive, so intensive that if you try to train this simple convolutional neural network with millions of images on a CPU, it'll probably take years to do it. These types of networks are trained on GPUs, not just GPUs, but GPU clusters, and in fact, tech giants like Microsoft and Google build and train CNNs like this, and they often spend hundreds of thousands of dollars in compute time in Azure, AWS, and elsewhere in order to train a simple neural network like this one. So while CNNs are fine in practice, to first order, they're really not that useful to me and you. They're only useful if you have the resources to train these models on very advanced GPU clusters. But the good news is you can benefit from CNNs as well, because Microsoft, Google, and others have already built very sophisticated CNNs, sometimes with hundreds of layers, and published them so that you or I or anyone else can use them. Most of these pre-trained CNNs are available on GitHub. They're also available through libraries like ML.NET and Keras. And because they've already been trained on millions of images, they're very good at doing what they do. Most of these were trained on 14 to 15 million images to recognize about 1,000 different objects inside an image: a hot dog, a hamburger, a cat, a dog, different types of cats and dogs and things like that. And because they've published these things for anyone to use, you and I can pull one of these things off the shelf and use it to do image classification without having to go through the training regimen. So as an example, back in 2014 or 15, one of the first really high-tech convolutional neural networks won a competition called the MLNET competition. The network was called VGG16. It was trained on more than 10 million images to recognize about 1,000 different objects. In other words, to look at an image and classify it in 1,000 different ways. If I wanted to use Keras to load VGG16 and run an image through it to have it classify that image for me, It's this easy to do. In Keras, I can simply call its VGG16 function to load the network. It actually goes out to a GitHub repo and loads it from there. It's about 50 or 60 megabytes, so the first download can take a little while. But once that network is loaded, I can then load an image of my own, one that I want to classify, and I can pass it to the model, to the VGG16 network by calling predict on that model. Then I can look at the results to see how it classified that image. So let's do that real quick. I'm going to pop out to, I thought I had that running. I guess I don't. Let's do it this way. What I'm going to do is open a Jupyter Notebook, which I happen to have installed on my machine. If you're not familiar with Jupyter Notebooks, they're really handy in that they allow you to enter and execute Python code in a very interactive manner. They're great for experimentation, for data exploration, data shaping, and things like that. And because I've installed the Jupyter Notebook runtime on my machine, I can load and run Jupyter Notebooks in my browser. The one that I want to run, and by the way, at the end of the session, I'll give you a pair of URLs where you can download all of these examples and more if you want. The one I'm going to run is one called Pre-Trained CNNs, where I basically do what you saw in the previous slide. This is Python code. I'm using Keras. I've installed Keras on my desktop machine in order for this to work, as well as TensorFlow. And I'm using Keras to load the VGG16 network, which has already been trained to recognize 1,000 different types of objects with a very high degree of accuracy. I then load an image of my own, one that contains this hot dog that you see right here. And I use code very much like the code you saw in the slide a moment ago to ask the VGG16 network to classify that image for me. And then I show the top 5 results that it came back with. It tells me that it is almost dead certain, almost 100%, that this image contains a hot dog. There's an infinitesimal chance the network believes that it contains a cheeseburger, and an even smaller infinitesimal chance it contains a French loaf. But because this network was trained with hot dogs, it's really good at recognizing that this image contains a hot dog. Now, one of the things that's kind of cool is looking inside the convolutional neural network, inside VGG16, to look at the feature maps that were generated by its convolution layers. With a little bit of work in code, not a lot of work, you can actually look at the feature maps that were generated. Now, the first layer, the first convolution layer of VGG16 generates 64 different feature maps using 64 different convolution kernels. I'm showing about half of those right here. These are the feature maps that it generated from the full-size image that I passed in. But then it ran that image through a pooling layer that cut it down to half of its original size, and it ran that through a convolution kernel to generate these feature maps right here. If you continue to go down, looking at the different feature maps that are generated at different layers in VGG16, you see that those feature maps become more and more fuzzy because the image is being subsampled and subsampled and subsampled again. But it is through these feature maps that VGG16 determines, okay, with these features right here, I think there must be a hot dog in that image, or there must be something else. Now, VGG16 is about 5 or 6 years old now. Since then, other convolutional neural networks have been built, trained, and published that achieve even higher accuracy in doing image classification. Microsoft produced something called the ResNet network. There are actually several different flavors of it. One of them is called ResNet 50 v2 because it has 50 layers. It's actually more accurate by a couple of percentage points than VGG16 at doing image classification. And by the way, it was trained on the same set of more than 10 million images to recognize the same 1,000 objects or classify images in the same 1,000 ways. So out of curiosity, what would happen if I used ResNet 52, which was built and trained by Microsoft Asia to classify that same hot dog image? Well, in Keras, I can easily load ResNet 50 v2. Once more, I load that hot dog image, And here I pass it into ResNet 50 v2 asking it to classify it. And I get slightly different results. It thinks that there's about a 99.87% chance that that image contains a hot dog. It also thinks there's a very slight chance it contains a pencil box, a corkscrew, a hair slide, whatever that is, and an abacus. So we got the same results with a different network, and you can see that if we were to look at these results, we would conclude that that image contains a hot dog. If this were a self-driving car, instead of looking for hot dogs, we might be looking for people or stop signs instead. But you've probably already thought about the downside to this. These pre-trained CNNs have been trained on expensive GPU clusters to recognize 1,000 different objects. What happens if we ask it to classify an image containing an object that it was not trained with, for example, sushi? So I take this sushi image, I pass it into ResNet 50 v2 and ask it, how do you classify it? Notice sushi doesn't appear anywhere in the list. It thinks there's about a 50-50 chance there's confectionery in that picture, or conch, as in conch meat or a conch shell, or a croquet ball or a balloon or a maraca, whatever that is. I think it's one of those shaker things. Problem is, because ResNet 50 v2, VGG16 and others were not trained with sushi images, they don't know how to recognize it. So it's cool that you can use these CNNs trained by other companies to perform image classification tasks yourself, but how do you make it domain specific? How do you build software that determines whether there's a person in the path of the crosswalk, sushi on a plate in a photo, or perhaps something else entirely, a defective part rolling off an assembly line? The answer to that question is a little bit of magic called transfer learning. Transfer learning allows us to have our cake and eat it too. It allows us to take these very sophisticated CNNs trained by Microsoft and Google and others and repurpose them to solve domain-specific problems. For example, to recognize whether the image that you pass into it contains sushi or a defective part or a person in a crosswalk or something like that. The beauty of transfer learning is we basically inherit the smarts of the network that's already been trained, but we don't really have to retrain it. We do a little bit of additional training with our domain-specific images, but because the vast majority of the work has already been done when the network was pre-trained, we can get sometimes very high degrees of accuracy, 95% or more, with a few minutes of training time on a laptop. It really does in some ways seem too good to be true, and yet it really works. Now, I want to show you graphically how transfer learning works. This diagram depicts the VGG16 network that we used a few moments ago. You can see the input layer on the left, several convolution layers followed by pooling layers that are successfully cutting the image down to size. And out on the right-hand side, you see the fully connected layers. This is where classification is performed, where the features extracted from the other layers in the network are looked at, and we decide, is there a hot dog, is there a piece of sushi, or what have you. By the way, all of those convolution and pooling layers are often referred to in the literature as feature extraction layers or bottleneck layers. So if I use the term bottleneck layer, I'm talking about all those convolution and pooling layers that extract features from the image. When I use the term classification layer in a CNN, I'm talking about the layers with conventional neurons out on the right-hand side that do classification based on the features that were extracted. The crux of transfer learning is that we take an existing pre-trained CNN like VGG16 or ResNet 50 v2 or whatever, and we load it, but we strip off and throw away the classification layers. So what we have at this point is a CNN that is very good at extracting features from images in various ways, but that doesn't know how to do any type of classification. Then we train our own classification layer that we append to the end of the bottleneck layer. So basically, we're allowing the bottleneck layers to do feature extraction the way they were trained to do feature extraction by Microsoft and Google, but by building our own classification layer, we are reinterpreting what those features mean. Maybe you see certain features in an image, and the way the network was trained, it interprets that as a hot dog. But we interpret it to mean, no, that's a defective part coming on an assembly line. That is transfer learning, and it works incredibly well. Now, how do you do transfer learning? Well, if you're doing it in Python with Keras, here is one way to do transfer learning. I load one of those pre-trained networks, in this case VGG16, but notice I've included an include top equals false attribute. That tells Keras to load VGG16, but to get rid of the classification layers at the end. I then go through the remaining layers, that's all the convolution and pooling layers in the network, in a for loop, setting each layer's trainable property to false. That means now if I take, say, 100 images and retrain the network with them, training is going to be fast because no training is going to be done in the bottleneck layers. The only training that will be done is in the classification layers that I add in. So then in Keras, I create a model that starts with VGG16 and then appends my own classification layers. In this case, one layer that is 256 neurons wide. Now I can do this. I can type in this code, I can run it, I can train the network with 100 or a couple of hundred images, and I should find that it's very, very adept at recognizing whatever it was I trained it to recognize. But there is a problem. This will train a lot faster than if you train the network from scratch, but it still won't train as fast as it could. In practice, when we do transfer learning, we use a little trick that makes transfer learning fast. The trick is this. We load the pre-trained CNN, in this case VGG16 again, but rather than incorporate its bottleneck layers in our own network, we take all of our training images and run them through VGG16 minus the classification layers. In other words, we pass all the training images through its feature extraction layers one time to extract features. Then we separately create our own neural network with the classification layers and train it with the features extracted from VGG16. If it's not obvious to you what the difference here, it is this. In the previous slide, if we train that network with 1,000 images, 1,000 images were being passed at least once, in all likelihood, multiple times through feature extraction layers just to generate the same results every time. And the feature extraction is CPU intensive, or I should say compute intensive. What we're doing here with this little trick is we're making sure that we only pass each image that we're going to train the network with through the feature extraction layers one time. Then we use the results to train our own classification network. This works. It tends to be super accurate, and it's very, very fast. If I, on a typical laptop, train this network with a couple of hundred images, it's probably going to train up in less than a minute or two, depending on what type of CPU you have and whether you have a GPU. So let me show you real quickly what transfer learning looks like with Keras, and then we'll come back and we'll do this in ML.NET. So to show transfer learning in Keras, I'm going to go back to my Jupyter notebooks. And I'm going to open a notebook called Transfer Learning. Again, I'll give you a pair of URLs so that you can download all of these samples and more for yourself at the end. So let me show you what I'm doing here. Let me first pop out to the directory where these notebooks reside, because I want to show you the images that I'm going to train this network with. So it's in my notebooks directory, and let's see, food, here we are. What I'm going to do is use 30 images. Whoops, that's not train, that's test. Let's go here. I'm going to train this network with 60 images, 20 hot dog images, 20 sushi images, and 20 pizza images. And then I'm going to use a separate set of 10 images of each to do my testing and validation to see how well it trained. Now, If I were to create a CNN from scratch and train it with just 60 training images, it would work, but I'd probably only get 65 or 70% accuracy, because to be incredibly accurate, remember, these CNNs are typically trained with at least hundreds of thousands and more often millions of images. But because I'm using transfer learning, I'm using an existing pre-trained CNN, I'm leveraging the intelligence it already has, I may achieve acceptable results in image classification with a mere 60 training images. Let's see if that's the case. What I do first is set up a little image pipeline in Keras. I'm using a Keras class called Image Data Generator. It looks inside that train directory that you saw, and it basically enumerates all the images in those subfolders and labels them according to the subfolder name. It's a quick and easy way to take a batch of images and label them by segregating them into separate subdirectories. I do the same do that for the training images, and I do it for the testing images as well. Once I've done that, I'm showing what some of these images look like, some of these hot dog images. Now you'll notice that they don't look like ordinary BGR images. When you use a pre-trained CNN, you use a function in Keras named preprocess input to preprocess the pixel values the way that CNN expects. Different CNNs are trained with input preprocessed in different ways, and Keras's preprocess input function takes care of that for you. It will do the preprocessing correctly if you're using VGG16, if you're using ResNet 50v2, if you're using Inception v3, or whatever. You let Keras do that for you. But the preprocessing for the network I'm using essentially converts the images from RGB into BGR, which is why they look a little bit funny right here. And again, that's important because I need to pre-process my images the same way the images that were used to train the network originally were pre-processed. I then create an instance of Microsoft's ResNet 50 v2, one of the most sophisticated image classification networks in the world, and I do exactly what you saw in the fast transfer learning slide. I run my training images and my testing images through the bottleneck layers of the network one time so that they don't have to be run through multiple times. Notice the include top equals false attribute. That's what's telling Keras, remember, that I want to load the bottleneck and feature extraction layers of ResNet 50 v2, but I don't want the classification layers. I then jump through a few hoops to generate the labels that I'm going to train and test with. I'm basically converting string labels like hot dog and pizza and sushi into categorical values, 0s, 1s, and 2s. Then I define my own very simple neural network, and I train it with the features that were extracted from ResNet 50 v2 when I pass my training and testing data to it up here. Now, it trains pretty quickly. You can see that a typical step was training in 7 milliseconds or so. Had this been a CNN we were training from scratch, each step with 60 images probably would have taken 10 to 20 seconds. You can multiply that to figure out how long it would take to train it if you had millions and millions of images. But because we're using transfer learning, we're not retraining all those convolution and pooling layers. Training is very fast. Here I plot the training and validation accuracy, and look at this. It looks like I'm getting up around 96, 97% accuracy in doing image classification, only training this network with 60 images, 20 images of each of 3 different objects. Now, let's take the network that we have repurposed. I don't want to use the word retrain, but the network that we've repurposed, and see if it can really identify things like hot dogs. So I was sitting out on my deck with my wife having lunch a few weeks ago. I grilled some hot dogs, and I thought, you know what, this would be the perfect opportunity to take a picture of my plate so that I can use it in some of my demos. So here are the 2 hot dogs that I grilled for myself that day. When I passed that through my repurposed CNN, it tells me that it believes with almost 100% accuracy that there is a instance of class 0 in that image. Well, what is class 0? do a little bit of work here to convert those categorical values, the 0s, 1s, and 2s representing hot dogs, pizza, and sushi, back into the string equivalents. And that network is fairly certain there's a hot dog in that image. But here's the rub. Here's the cool part. Remember when we used a pre-trained CNN to identify an image containing sushi? It had no idea what to do because it wasn't trained with sushi. I'm running that same sushi image here through my repurpose network, and it tells me with near 100% accuracy that that image contains sushi. So transfer learning allows us to take very sophisticated, already trained convolutional neural networks and repurpose them to solve domain-specific image classification problems with relatively few training images and with very little CPU power required. That is the crux of fast transfer learning. It is the staple of self-driving cars and things like that, and Keras and Python is one way to do it. Now let's turn our attention to ML.NET. There are a lot of reasons that I love ML.NET. One is that even though I do a lot of programming in Python these days, Python is not my language of choice. I use it because there are a lot of great data science, machine learning, and AI libraries available for Python. My favorite language for 20 years has been C#, and given a choice, I will always code in C# rather than Python. So you may be aware that Microsoft a couple of years ago introduced an open source library called ML.NET. It's kind of like scikit-learn, if you will, which is a very popular Python library for machine learning, for .NET and for C# developers. So today, if I want to build sophisticated ML models, rather than resort to Python and scikit-learn and other libraries, I can do it in C# natively using ML.NET. Now, here's something interesting. ML.NET is very, very good at helping you build non-deep learning models, traditional machine learning models that use gradient boosting machines, support vector machines, and other learning algorithms. ML.NET is not like Keras. It's not designed to help you build neural networks or convolutional neural networks from scratch. But because transfer learning is so important in the world of ML and AI, ML.NET makes transfer learning super easy. In fact, easier than Keras. I will go so far as to say that no machine learning library today makes it as easy to do transfer learning as ML.NET does, especially in version 1.4 and higher. Because in version 1.4, they introduced a class named Image Classification Trainer. You could do transfer learning with ML.NET prior to 1.4, but there was more code and more expertise required. You had to go out and separately find and load the TensorFlow network that you were going to use, VGG16 or ResNet 50 or Inception V3 or something like that. And you had to have a fairly intimate understanding of that network's architecture and the names of the layers and things like that. With the image classification trainer class, all of that is abstracted away. If you can sling 10 or 15 lines of C# code, you can build super sophisticated image classification networks by using ML.NET to do transfer learning on top of pre-trained CNNs made available by Microsoft, Google, and others. And by the way, when you repurpose these CNNs with transfer learning, you can do it on CPU or GPU. If you want to do the retraining on a GPU, then you just install a different NuGet package in your ML.NET project. So I want to show you a couple of slides here with some code that shows the basics of how ML.NET makes transfer learning super easy, and then I'll show you an actual app that uses this. The first thing I need to do if I'm using ML.NET to do transfer learning is I need to load the images that I'm going to train it with. Now there's an infinite number of ways you can do this, but what we often do and what I do is something like this. I write a little method, and I'll show you this in my next sample, called load labeled images from path, which takes a path and will enumerate the subdirectories inside it and the images inside those subdirectories. Then it will label those images by the subdirectory names. Essentially the same thing that we accomplished with the image data generator class that's built into Keras. So I call my own load labeled images from path method. That returns an IEnumerable. I call load from enumerable in ML.NET to convert the IEnumerable into an iDataView, and then I shuffle the rows in it because I want to make sure that basically the rows are in random order. I don't want all hot dog images followed by all pizza images, all sushi images, etc. I randomize those by shuffling them. Then I need to do one other thing. I need to convert those labels, which are strings, hot dog, pizza, sushi, into integer categorical values. You may have done this before in ML.NET. If you haven't, we typically do it by doing what I'm doing here. I call ML.NET's map value to key method. I'm simply converting, again, those string labels into integers. Then I call ML.NET's load raw image bytes method. This is where it actually goes out and loads the images. By the way, in my load labeled images from path method, I'm not actually loading the images. I'm just creating an IEnumerable of objects that contain the paths to the images. It's inside load raw image bytes that the images actually get opened and read and prepared in order to do transfer learning. Once I have the images loaded, transfer learning is this easy thanks to the image classification trainer class. I first create an image classification trainer options object. Now I'm only using here 5 of probably 15 to 20 different options, but this is where you specify a lot of important things, including which pre-trained CNN you want ML.NET to use. You don't have to go find these things separately on GitHub or elsewhere because ML.NET loads them for you. Here, I'm asking for it to use Microsoft's ResNet 101 v2 network, which is also one of the most sophisticated ones in the world. Then, when I create my ML.NET pipeline, I simply include that image classification trainer, and I add one more call to map key to value to take the predictions, the 0s, 1s, or 2s, indicating whether this image contains a hot dog, sushi, or pizza, to the predicted label of the output class. And finally, as I always do in ML.NET, I call fit to train the model. Training is very fast because it is transfer learning. Let me show you an example. I'm going to pop out to Visual Studio here, and I'm going to load first an ML.NET project that trains or retrains or repurposes that ResNet 101 v2 network. And here's what it looks like. So I start by calling my own load labeled images from path method like you saw on the slide. Here's what that method actually does. It simply returns a collection or a list of input objects. I've defined the input class this way. Each one contains the actual image bytes eventually, not initially, but eventually, the path to the image, and the string label for the image, hot dog, pizza, sushi, or what have you. All I'm doing is looking at the path, in this case to the data folder, enumerating the subdirectories inside it, then enumerating the files in the subdirectories and creating input objects that I'm adding to this list. So I return the list, then I wrap an iDataView around that list by calling ML.NET's load from enumerable method. Then I do the exact thing that you saw in the slides. I convert those string labels into integer categorical values, and I ask ML.NET to actually load the images for me. It's at this point that it reads the images and copies their bits and bytes into the image property of the input object. Then, as I often do in ML.NET, I do a train test split. Do an 80-20 split on my data set. That way I can train it with 80% of the data, test it with 20%. And then, again, as you saw in the slides, I'm creating an options object. I'm specifying which pre-trained CNN I want it to use. A few other things, including, hey, rather than let ML.NET split off part of the training data set that I give it to do testing, I've already done that. So I say test on train set equals false and use the options object's validation set property to point it to the test data that I split off up here. Then I train the model, and I won't do this in real time. It takes a couple of minutes, which is pretty remarkable, but I'm using the same 60 hot dog, pizza, and sushi images to do the training here that you saw in the Keras example. What is ultimately output here is a zip file. Let's go take a look at it. I think it's around 50 or 60 megabytes with that repurposed network, the one that was repurposed with transfer learning. Let's do this. Let's just go on to the final demo, because we don't know that this thing works unless we actually try it. So what I've done is I've built a little WPF app that on startup loads that model that I trained and saved out to the zip file in my model folder, and then allows me to browse the file system selecting images, and then it runs the images that I select through the network that I retrained in order to classify them. Let's look at an example or two here. So here's the app. I'm going to load first that hot dog image that I took on my deck a few weeks ago. And when I run it through this retrained network, it tells me with 99.9% certainty it believes it sees hot dogs in there. What if I try this pizza image? Pulled this off the internet this morning, just a random pizza image. 99.9% sure it contains pizza. What about that sushi image? Remember, the original network, the pre-trained CNN I used, doesn't know anything about sushi. It had never seen it. But because while doing transfer learning, I trained it with 20 sushi images, now it has a pretty good idea of what sushi looks like, and it tells me that it's 98.3% certain that this image contains sushi. So these examples are perhaps a little bit frivolous, given that, let me go back to PowerPoint here, given that I'm just classifying images by food groups, essentially. But remember, you can generically use this technique to train or repurpose, I should say, a pre-trained CNN to do almost any image classification task you want. Transfer learning is the secret, and no library makes it easier than ML.NET. Now, if you would like these examples that I showed today, there are two public GitHub repos you can go to. One of them is my deep learning repo. The other is my ML.NET repo. There are lots and lots of samples there that you're free to download and use as well, in addition to the ones I showed you. Do check back on those repos from time to time, because I'm constantly adding new samples and updating existing ones. So I think our time is up. I hope that you learned something here. Hope you found the time useful. If you have questions, if you try this for yourself and run into issues, feel free to reach out to me. Be happy to answer your questions if I can.
Thank you, Jeff. But I have to say it was very cruel of you. I mean, Florian is here for more than 6 hours on coffee alone, and then you train your network with food images.
When I'm going to dream for a couple of hours.
Well, I know that this is a long day for both of you. It's also a great day. I want both of you to go out and treat yourself to a great dinner tonight, okay? Hot dog, pizza, and all the sushi you can eat.
Okay. So it's been really an outstanding presentation. So I personally learned a lot from it. The first question now that comes to my mind is, what do you do at Wintellect? You're a co-founder of this company.
Yes, that's a good question. What do I do at Wintellect? So I do a lot of things. I do a lot of work in our training division, writing courses, delivering courses, and things like that. We also have a consulting division, which is actually quite a bit larger than our training division. And I help out over there some, but for the most part, they like me to stay over in the training side. So I spend a lot of time doing research, a lot of time writing materials for Wintellect and for Microsoft. I still do a lot of that. And I have a lot of fun because I get to learn new stuff.
Which is great. I'm sure all of the projects are really interesting, but anything that comes out in your mind that you want to share, maybe related to the topic that you...
Yeah. So one thing that's really interesting is in the consulting division at Winelect, increasingly we're having customers contact us who are not just wanting software written, but they want to know how ML and AI can be used to solve problems. And I love listening to these customers and coming up with solutions. Just one quick example, we got a call from a customer last year. They basically have a document management system. They process hundreds of thousands, sometimes millions of invoices a year from their vendors. And they're required by law to review each of those invoices for fraud. But there are like 3 people in the office to do the review, so they can't possibly do it. So they came to us and said, can you build a system for us that uses AI to look at every invoice that comes in and flag the ones for us that are likely to be fraudulent so that we can turn our attention to them? So we said, sure, we'd love to look at this. So one of the first things we did is we asked them, what makes an invoice fraudulent? What kinds of things characterize a fraudulent invoice? One of the answers they gave us was, well, fraudulent invoices often have important lines redacted, where someone has literally crossed it out with a thick magic marker. 20 years ago, it would have been difficult for us to write software that looked at a scan and tells you whether it's redacted. Today, with transfer learning, it's easy to train a CNN to recognize whether a scanned document contains redacted data. So that's one example right there, and we get these calls just about every week, and it's awesome. One of the things that I'm seeing is software developers are realizing that AI and ML open up whole new frontiers. We can build software that's smarter than ever before because we can now do things that we cannot do algorithmically. It really is a new way of thinking about software.
And getting back to, thank you, really relevant. And then getting back to our talk, it's even, like I said, it's even better now that there are tools like ML.NET where, you can employ your language of choice or your knowledge of the language to write and to write your code and in this manner.
Yes, well, and I assume a lot of people who are attending Code Camp are .NET developers. They prefer C# like I do. ML.NET to me is just amazing. It's exciting. It's overwhelming because finally I have a world-class library for building these models in C# rather than Python. So I love ML.NET.
I was impressed myself. Then we have a very specific question. So the question is, TensorFlow has a so-called placeholders for input variable data at some time
later.
Yeah, in the pipeline. Many models have them. How or where can we fill these placeholders in ML.NET pipelines?
That's a great question. So I'm not familiar with placeholders in TensorFlow. I've never heard of them. So I will tell you this. Whatever these placeholders are, and I think they're in the input layer, did they say?
Yes.
Yep. Whatever they are, I can tell you this. You cannot build neural networks from scratch with ML.NET. So it's not an issue if you're building from scratch. You can consume TensorFlow models that have already been built and trained in ML.NET. Whether it has cognizance of those so-called placeholder values, I don't know. I'll have to do some research myself to find out what a placeholder is in TensorFlow.
Thank you so much.
Yep.
All right.
Okay, Jeff, thank you again for being with us. Hope to do it also in the future. And have a great day for you. It's just starting.
Thank
you as well, and good luck the rest of the day. Thank you for inviting me to speak. Have a good one.
Thank you so much.